Every wedding ring on Earth has a crime scene. 10 billion trillion tons of gold, forged in under 2 seconds, inside a collision so violent it shook the shape of space itself. Where does gold come from? It did not come from the ground. It did not come from volcanoes. Nothing on this planet is violent enough to forge it. Gold is made when dead stars collide. On August 17, 2017, 3 detectors on 2 continents picked up a signal that had been traveling for 130 million years. LIGO, the Laser Interferometer Gravitational Wave Observatory, registered a ripple in space itself. 1.7 seconds later, the Fermi Gamma Ray Space Telescope caught a burst of high-energy light from the same direction. Within 11 hours, 70 telescopes on every continent pointed at a single patch of sky in the constellation Hydra. What they found was gold being manufactured in real time. Astronomers cataloged the event as GW170817. It was the first neutron-star collision ever witnessed by human instruments in both gravitational waves and light. And it tore open a question that had haunted physics for 60 years. How is gold made in space? 3 camps had been fighting over that answer for decades. One group said supernovae, the explosions of massive dying stars, produced all the heavy elements. A second group said no, only a neutron-star merger could generate enough force. A third group said both contribute, but nobody could prove the ratio. Before that night in August, it was theory against theory, model against model. After that night, there was physical evidence. By the end of this video, you will know exactly what happened inside that 2-second window, which camp the data supports, and why the answer changes what you think you are made of. Start with the crime scene itself. 2 neutron stars, each roughly the mass of our sun, but crushed into a sphere about 20 kilometers across. That is the width of a mid-sized city. A single teaspoon of material from either one would weigh about 1 billion tons on Earth. These are not normal objects. They are the exposed cores of dead massive stars, left behind after supernova explosions stripped everything else away. Nothing but neutrons, packed so tightly that the atoms themselves have been destroyed. Protons and electrons forced together under pressure that no laboratory on Earth can replicate. 2 of these objects had been locked in orbit around each other in a galaxy called NGC 4993, 130 million light-years from Earth, spiraling inward, losing energy into gravitational waves with every pass, getting closer by fractions of a millimeter per orbit for millions of years, with no one watching. For longer than complex life has existed on Earth, these 2 dead stars were falling toward each other, sending ripples through space that no instrument could detect. The inspiral takes hundreds of millions of years. The collision takes 2 seconds. That ratio, millions of years of silence followed by 2 seconds of creation, is one of the most extreme contrasts in nature. The final minutes changed that. The orbit tightened beyond recovery. 1,000 revolutions per second, then 2,000. The gravitational wave signal climbed in frequency, a pattern called a chirp, because when converted to sound, it rises in pitch like a bird call, accelerating into a scream. LIGO caught the final 90 seconds of that signal. The waveform told physicists exactly what was falling inward. 2 objects, one roughly 1.17 solar masses, the other roughly 1.6 solar masses. Both were within the narrow mass range that only neutron stars occupy. Not black holes, not white dwarfs, 2 dead star cores. Contact happened at roughly 1/3 the speed of light, about 100,000 kilometers per second. 2 city-sized objects, each heavier than the sun, hit each other with enough energy to release roughly 100 times more energy than our sun will emit across its entire 10 billion year lifetime. The collision did not look like a Hollywood explosion. There was no single blast. The physics was closer to 2 water balloons made of nuclear matter slamming together at an impossible speed. The outer layers sprayed sideways in long tidal streams. The cores merged. Material launched into space at 20 to 30% of the speed of light, and something formed at the center that physicists are still fighting over. But first, the response on Earth. Within 1.7 seconds of LIGO registering the gravitational wave, Fermi caught the gamma-ray flash. The automated alert system fired. 11 hours later, a team using the SWOPE telescope at Las Campanas Observatory in Chile found the optical counterpart, a new point of light in the galaxy NGC 4993 that had not been there before. By the next morning, the European Southern Observatory, the Hubble Space Telescope, the Chandra X-ray Observatory, and dozens of ground-based instruments across every continent had locked onto the same coordinates. Radio telescopes joined 9 days later when the signal finally became detectable at those frequencies. 70 observatories in total covered gravitational waves, gamma rays, X-rays, ultraviolet, visible light, infrared, and radio. No single event in the history of astronomy had ever been observed across that many instruments and that many types of light simultaneously. This was not a discovery. It was a coordinated forensic reconstruction, assembled in real time by thousands of scientists who knew they were watching something that would not repeat for years. Here is where the investigation splits. When those two neutron stars merged, what survived at the middle? The first camp, backed by digital crash test reconstructions of the collision, says a black hole formed almost instantly, within milliseconds. The combined mass of the system exceeded the upper limit that any neutron star can support. The core simply collapsed. Gravity won. End of story. The second camp looked at the same event and reached the opposite conclusion. Their evidence was the kilonova itself, the visible glow from all the material thrown outward. It was too bright. Too much matter had escaped. If a black hole had formed in milliseconds, its gravity should have swallowed most of that material before it could get away. The kilonova light curve required more ejecta than an instant collapse can explain. Their reading was that something survived at the center. A hypermassive neutron star, spinning thousands of times per second, supported itself against collapse through pure rotational force for perhaps a full second, maybe longer. During that borrowed time, it acted like an engine. Magnetic fields and rotational energy drove additional material outward, feeding the kilonova, before the neutron star finally gave way and collapsed into a black hole. This is not a minor disagreement. A surviving neutron star at the center means more material ejected. More material ejected means more gold produced. The total yield of heavy elements from GW170817 depends directly on which camp is correct. Same collision, same instruments, same data, two fundamentally different pictures of the engine that powered it. The gravitational wave signal from LIGO cut off cleanly after the merger, which supports instant collapse. But the optical and infrared light stayed bright and evolved in a way that suggests extra energy input, which supports delayed collapse. As of today, neither reading has been eliminated. The next detected neutron star merger may settle this, or the next one after that. Now, the gold. This is the forensic core of the entire case. Explained simply, a kilonova works like this. When two neutron stars ripped each other apart on contact, they flung a cloud of material into the surrounding space at a significant fraction of the speed of light. That cloud was almost entirely neutrons, pure neutron-rich matter, the densest, naturally occurring substance in the known universe, suddenly released from the crushing pressure of the star that had held it together. When free neutrons at those temperatures and densities meet seed nuclei, the R process begins. R stands for rapid neutron capture. Here is how it works. A seed nucleus, perhaps iron or something close, sits in a bath of free neutrons, traveling at extreme speed. That nucleus captures one neutron, then another, then dozens in milliseconds. Each captured neutron makes the nucleus heavier and less stable. Eventually, the bloated nucleus cannot hold together and undergoes radioactive decay, converting a neutron into a proton. That single conversion shifts the element one slot up the periodic table. Then the capture cycle restarts. More neutrons slam in, more decay follows, more climbing. In under 2 seconds, this chain of captures and decays builds elements that no star, no ordinary explosion, and no other known process in the universe can produce. Gold, platinum, uranium, thorium, iodine, xenon, neodymium. Every element heavier than iron on the periodic table traces its origin primarily to this mechanism. The speed is staggering. The entire construction, from bare neutrons to finished gold atoms, completes before the collision debris has traveled more than a few hundred kilometers from the merger site. Think about that in terms of what you already know about gold. Humans spend years digging it from rock. The R process produces more gold in 2 seconds than every mine on Earth has produced across all of recorded history. The collision does not care about scarcity. It produces heavy elements the way a fire hose produces water, violently, briefly, and in quantities that dwarf any human frame of reference. The core collapse took under 1 second. The neutron ejection took seconds. The R process ran for milliseconds within that window. The resulting kilonova glowed for weeks as those freshly built elements decayed. 4 timescales for one event, and each timescale left a different kind of evidence for the 70 telescopes that were watching. Now the second camp was at war. Supernovae had been the assumed answer for where heavy elements come from for most of the 20th century. Textbooks printed it as settled science, and professors taught it without qualification. The reasoning felt solid. Massive stars explode when they die. Those explosions carry enormous energy. Energetic environments should forge heavy elements. But when physicists actually ran detailed computer models of supernova explosions through the 1990s and the 2000s, the numbers kept coming up short. Supernova produce staggering energy, yes, but the neutron-rich conditions required for the R process were too brief and too diluted in standard supernova models. The heavy element output was a fraction of what the Milky Way actually contains. The neutron star merger camp had the math on their side. The conditions inside a kilonova are almost perfectly tuned for the R process, enormous quantities of free neutrons, extreme temperatures persisting for the right duration, material ejected fast enough to avoid falling back. One neutron star collision produces more heavy elements than thousands of supernovae combined, and for years, this was a theoretical argument with no direct test. GW170817 was the test. 70 telescopes watched the kilonova fade over the following days and weeks. The specific colors of light shifted in a precise pattern that matched theoretical predictions for a cloud of newly minted heavy elements undergoing radioactive decay. In the first 2 days, the kilonova glowed blue. That blue light came from lighter R process elements, the ones between strontium and silver, decaying rapidly near the surface of the expanding cloud. By day 4, the glow shifted to red. The red came from deeper inside the debris, where heavier elements like gold, platinum, and the rare earth metals were decaying more slowly. The color change itself was the diagnostic. Blue to red, fast to slow, light elements on the outside, heavy elements on the inside. Exactly the layered structure that our process models had predicted for decades, but nobody had ever directly confirmed. The kilonova's glow was not from the collision energy. It was the radioactive afterburn of freshly created heavy elements cooling in the expanding debris field. That color evolution was the single most important piece of evidence in the case. Not a model fit, not a simulation output. It was a direct measurement, tracked night after night, matching predictions to a degree that left very little room for alternative explanations. But the supernova camp did not concede, and their objection was legitimate. Neutron star mergers are genuinely rare. For 2 neutron stars to collide, they must first form as a pair orbiting the same center. Each one is born from a massive star that dies in a supernova. The pair has to survive both explosions without being flung apart. Then the 2 remnants must spiral together over millions to billions of years. Estimates suggest the Milky Way hosts roughly 1 neutron star collision every 100,000 years. The supernova camp asked the obvious question: can events that rare account for all the gold and platinum in the galaxy? Based on GW 170817, the answer appears to be yes. Models estimate that one collision produced billions of trillions of tons of gold. The total heavy element yield was roughly 16,000 Earth masses. The sheer volume from each collision compensates for the low frequency. But galactic chemical evolution models, the computer simulations that track how elements build up across billions of years of star formation and death, still struggle to reproduce every observation with mergers alone. Some researchers argue that a specific type of supernova called a collapsar, a rapidly spinning massive star that collapses directly into a black hole while launching jets of material, contributes an additional fraction of heavy elements. The Collapsar argument gained ground in 2019 when a team published simulations showing that the jets from these collapsing stars create pockets of neutron-rich material dense enough to run the R process. Not as efficiently as a neutron star merger, but frequently enough to matter. Collapsars happen perhaps 10 times more often than neutron star collisions. If each one produces even a small yield of heavy elements, the cumulative contribution across billions of years could fill the gaps that mergers alone leave in the chemical record of the galaxy. The merger camp pushed back hard. Their objection, Collapsar R process yields, depend heavily on assumptions about magnetic field geometry inside the jet. Change one parameter by a factor of 2, and the heavy element output drops to nearly 0. The Collapsar contribution, they argue, is model-dependent in a way that the kilonova contribution is not. GW 170817 was a measurement. Collapsar R process yields remain a simulation. Nobody has nailed the final ratio. Neutron star mergers produce the majority, and on that point, almost everyone agrees. Whether the split is 90% mergers and 10% collapsars, or 99-1, or 100-0, remains genuinely open. That is an honest statement, not a hedge. The raw scale of what happened deserves a clean accounting. 2 neutron stars, each about 20 kilometers wide, each heavier than the Sun. Collision speed, 1/3 of the speed of light. Duration, under 2 seconds. Ejecta mass, roughly 5% of a solar mass. That 5% contained several Earth masses of gold, along with comparable quantities of platinum and other heavy elements, totaling roughly 16,000 Earth masses of our process material. The platinum and uranium yields are harder to pin down because their radioactive signatures overlap with other heavy elements in the infrared data, but models place them in a similar range. Earth holds roughly 190,000 tons of gold extracted by humans across 6,000 years of continuous mining. Every bar in every central bank vault, every coin ever struck, every circuit board ever manufactured, every ring, chain, and tooth filling on the planet. 190,000 tons. 1 kilonova produced more gold in under 2 seconds than humanity has mined across all of recorded history, multiplied by a number so large it stops meaning anything. The numbers get stranger the longer you sit with them. Gold is considered rare on Earth. Wars have been fought over it. Economies have been built around it. People have died in mines trying to extract it from rock. One collision between 2 dead stars, lasting less time than it takes to blink, produces enough of it to make the entire concept of scarcity meaningless on a cosmic scale. If all of Earth's mined gold were gathered and melted into a single cube, that cube would measure roughly 22 meters on each side, small enough to fit inside a tennis court. A single kilonova would produce enough gold to fill a volume larger than some of the smaller moons orbiting Jupiter and Saturn. GW 170817 is one collision in one galaxy 130 million light-years away. The observable universe is 13.8 billion years old. Across that span, in hundreds of billions of galaxies, billions of neutron star mergers have occurred. The cosmos is filled with the debris of these collisions. We are standing in it. This is where the evidence reaches you personally. There is gold in your blood, roughly 0.2 milligrams of it, dissolved in your bloodstream at this moment. Not metaphorically, measurably. Medical tests can detect it. That gold was not made on Earth. It was not forged in the sun. It was created inside a neutron star collision, billions of years before our solar system existed, ejected at a quarter of the speed of light, and scattered across a region of space that would eventually collapse into the cloud of gas and dust that became our solar neighborhood. You carry trace amounts of a kilonova inside your veins. The iodine in your thyroid gland has the same origin. Without our process iodine, the human thyroid cannot function. You would not be able to regulate your own metabolism without material that was produced in a collision between dead stars. The platinum used in chemotherapy drugs that have saved millions of lives has the same origin. Forged in the same type of event, scattered into the same type of dust cloud, billions of years before it was needed. The gold in your wedding ring traveled through interstellar space for billions of years before arriving on a planet that had not formed yet. It was embedded in the original dust cloud that produced the sun and the rocky worlds. It survived gravitational collapse, planetary formation, the heavy bombardment era, and 4.5 billion years of geological recycling. Someone pulled it from the ground without knowing what it was or where it came from, and now it sits on your finger. A piece of a collision between two dead stars, older than the Earth, older than the Sun, older than anything in this solar system. Imagine tracing a single atom of that gold backward, past the mining, past the geology, past the formation of Earth, past the birth of the Sun, back through billions of years of drifting through empty space. And then you arrive. Two neutron stars, city-sized, sun-heavy, slamming together at 1/3 of the speed of light. A flash of gravitational waves. A spray of the heaviest elements nature can build. Your atom of gold, brand new, 2 seconds old, launched into a universe that would not produce your planet for another 8 billion years. That is a kilonova. That is how gold is made in space, not gently, not slowly. In a collision so extreme, it bent the shape of space, lit up every major observatory on Earth, and produced more gold in 2 seconds than this planet contains in its entire crust, mantle, and core combined. All of us know this because on one night in August 2017, for the first time, we caught it happening. The evidence is still being weighed. LIGO began its 4th observing run in 2023 with upgraded sensitivity that expanded its detection range for neutron star mergers by roughly 40% compared to the run that caught GW170817. As of this recording, that 4th run has detected additional candidate mergers, but none yet with an electromagnetic counterpart as complete as GW170817. The upgraded instruments are listening. The universe has not given all of us a second clean crime scene. When the next one arrives, LIGO and its partner detectors Virgo in Italy and KAGRA in Japan will capture it with higher precision than anything recorded in 2017. Each new detection is another crime scene. Each one tests the models. The question of what forms at the center, black hole or surviving neutron star, will eventually be answered by statistics. One event can be interpreted either way. 10 events will show a pattern. The question of whether collapsars contribute to heavy element production will require a different kind of evidence, probably from the chemical fingerprints of ancient stars that formed before neutron star mergers had time to enrich the galaxy. Those measurements are already underway using the James Webb Space Telescope and ground-based instruments, like the Extremely Large Telescope, under construction in Chile. The gold question is the most productive open case in astrophysics right now. Every answer keeps pointing back to that same 2-second window. There is another force acting on the universe right now, something that produces no light, no heat, no radiation of any kind. It is pulling every galaxy in our region of space toward a single point at 450,000 miles per hour. It sits behind the thickest part of the Milky Way, hidden from any direct observation. Astronomers call it the Great Attractor. After 50 years of searching, nobody can say with certainty what it is. That case is next.